So, next speaker is Paola D'Aquino from the University of Campania, Vanvitelli, of Roots of Exponential Polynomials.
First of all, I would like to thank the organizers for giving me the chance of giving this talk, which means to be here. And second, I apologize because the topic is not related to the main topics, to the mainstream of the other talks. Nevertheless, I hope you will find something interesting. So, I just say what an exponential polynomial over the complex field, or more in general, what we see later, is just an expression in like this one. This is two iterations of exponentiations. There are various approaches. What can we study about these polynomials? I will concentrate, I don't know if I will have the time also to discuss the three main topics, goals I wrote down, to understand the zero sets of an exponential polynomial, to understand the nature of the zero set of an exponential.
So it is a definition or an example?
Example.
Example, okay.
And I will not give the definition. I will not give the definition, otherwise it will be too long. And then the intersection of the zero sets of two exponential polynomials. I will say a few things. Now, what is an exponential ring? Is just a pair where R is a ring, always commutative for us, and it can be also a field. In that case, I could call it as an E-field. And then there is, which is equipped with an extra function, which goes from the additive structure into the multiplicative structure of the invertible elements. So these are the invertible elements, and which satisfies the basic laws of exponentiation, 0 to 1, and the exponential of a sum is the product of the two exponentials. Some examples. There is always, I concentrate first on the second one, which is not interesting at all. If you take a ring, you send everything to 1, this is an exponentiation, but of course it's not interesting. The most known ones are the reals with exponentiation, the complex field with exponentiation, so this we all studied, at least you know what they are. Then there is the ring of exponential polynomials, where I can put an exponential on it, and this is what you ask, and I'm not going to say what it is, but the idea is that you iterate exponentiation. And this is in any number, finite number of variables. Basic things, if you start with a domain, also the ring of exponential polynomials is an integral domain, and the units can be characterized as those products of an invertible of the domain you started with, and the purely exponential thing. And an element, as classically is said in a ring, is irreducible if there are no known units, G and H, such that F is the product of this GH. This is an example of an irreducible polynomial over R or over C. It can be proved that it is irreducible.
Paola, I'm trying to understand this definition of units. So it seems that you say that it's an integral domain whose units are from U, or it's exponential of an exponential. Okay.
Yes, I'm characterizing the units of the in the ring. This one is all the polynomials. Sorry, here there is a bar, and here there wasn't, but I mean the same.
You use all the two non-algebraic constants, pi and e. I see pi there.
Yes, over the complex field, for example.
All the non-algebraic constant that you use, or some other.
This is just an example of an irreducible polynomial. It's nothing else. Just there are, and this is one example. So, an analysis of the most important exponential fields, the reals and the complex field. which motivates, at least for me and for many other people, the work on these exponential polynomials. Now I've divided in two parts. On the left there is what is, everything is understood about the reals with exponentiation. So this is it has a decidable theory modulo this SC, which I will explain in the next slide. This is a conjecture, Shermer conjecture, which comes from transcendental number theory. The theory of the reals with exponentiation is model complete. Then we know now what it is, thanks that you introduced this morning. And the reals with exponentiation is minimal, which means that there is a good description of all the definable sets in one dimension, and as a consequence also in higher dimension. And this is mainly work done by Wilkie and McIntyre. Then we go to the corresponding field, complex field. And because you can define the integers in this way, then the theory of the complex exponential field is undecidable. It's not model complete. And there are, these in red are open questions, the basic open questions. And this corresponds, quasi-minimal means that the definable sets, unary definable sets, are countable and co-countable. It's not known. Since you can define the integers, which is countable, so you can define the complement. So the idea is maybe is quasi-minimum, but it's not known. It's not known what are the automorphisms of C with exponentiation, and of course these are all strictly connected. It's not known if the reals are definable in Cx. So this motivates. So I recall what Shermer conjecture says is that if you take, it starts of course from the complex field, you take complex numbers, and it says just that the transcendence degree of the 2n tuple, you give as an input the complex numbers and the exponentials of this. So the transcendence degree has to be greater or equal than the linear dimension. This is a generalization of Lindemann-Weierstrass theorem, which says that if you take algebraic numbers which are linearly independent of the rational numbers, then the exponentials are algebraically independent. And also as a consequence is that if you take alpha, an algebraic number, then e to the alpha is transcendental. And this is proved, of course. There are cases which are true. I just listed some. Maybe these are of course very old. This one is a bit more recent by Nesterenko, who proved that as a result is that the pi and e to the pi are algebraically independent over Q. And also Shermer conjecture is true for the ring of power series over C. This is due to us in 71. So there are cases, but the full Shermer conjecture is still open, and it's accepted. For maybe this is the thing which could be, this slide could be related to the main topic of the conference. There are these two definitions. The first one, due to McIntyre, goes back to 96, an existential definition of the rationals, and inside the complex field, complex exponential field, and in as the quotient of two periods. These periods mean the kernel of exponentiation. And Laskovich in 2002 found an existential definition of the integers using, for this one I mean the above formula here. So the theory, the existential theory of Cx is also undecidable. Now the model theoretic analysis of this structure, so we know that there is, we know that there is that the complex field is the canonical model for the theory of algebraically closed fields. of characteristic 0 and cardinality to the left 0. This is the unique one. And the question which Zilber asked was if there is an analog of this for the exponential counterpart. I mean, is the exponentiation that we know over the complex field a unique one? So in order to do this, to study the structure, because it was not known almost anything about CX, Zilber introduced a new class of exponential fields, which he refers, and I try to refer to his name as pseudo-exponential fields, and he found an axiomatization. Now, in the next slides, there is an axiomatization. I will not comment on all single axioms, because it would take too long. I will just say what the idea are. So he finds this axiomatization, which is reported here. So, of course, he gets inspired by the complex field. So you want that is an algebraically closed field of characteristic 0. You want that exponentiation is a surjective homomorphism from the additive structure to the multiplicative structure, okay? And you want that the kernel is cyclic, infinite cyclic, generated by transcendental elements. Then you want that the Shannon conjecture holds, and this is the whole condition, is the same one as I explained before. And these two axioms are the crucial one, especially these four axioms, which says that if you take a variety, this V a variety, with, under certain hypotheses which I'm not going to say a single word on, this intersects the graph of exponentiation into a generic point. And I will come back on this because it's the main topic I will talk about. And then there is the last axiom, which says that there must be these generic points, but there cannot be too many, only countably many. So Zilber proves on this class of structures that it's categorical in each uncountable cardinality. So there is a unique model of each uncountable cardinality. These fields of his are quasi-minimal, so every definable set is countable, or the complement of a countable set. And there are many automorphisms. So for the pseudo-exponential fields, all these three questions, are answered. And so his question is this, on C there is the usual exponentiation that we know, and there is a Zilber exponentiation. And the question is if these two are isomorphic, so if the unique pseudo-exponential field of cardinality to the reality 0 is the classical complex exponential field. This is still open, we don't know. And this has motivated all the research on these exponential polynomials in connection with this strong exponential closure. Because Zilber proved that for the complex field, this property, the countable closure property, holds. So the only thing, modulo Shannon conjecture, the only open problem is still this, is only this one, the strong exponential closure. No, I'm sorry. Okay. So the problems are, you can approach the question in two different ways. You ask, does CX satisfy properties which follow directly from the axioms of Zilber? Mainly, also if CX satisfies all the axioms of a pseudo-exponential field. And or vice versa, does C the exponentiation Ala-Zilber satisfies properties which are known from complex analysis, for example. Of course, you cannot reproduce complex analysis here. You have to find in here. You have to find other methodologies, other tools, and other techniques. So Zilber proved that, as I said before, Cx satisfies the countable closure property. And so modulo Sharma conjecture, the strong exponential closure is the only obstruction to answer the main, this one. So there is a characterization of exponential polynomial of any height here, any height whatsoever. Many iteration exponentiation due to Hanson and Rubel, which goes back to 84, which characterizes those exponential polynomials with no solution. So these are pure exponential terms, pure exponential polynomials, and where this G is in turn an exponential polynomial. And to do this, they use Nevallina theory, so analytic methods. Katzberg in 83 characterized those exponential polynomials which have only finitely many roots, and so it's of this form. These are linear polynomials which give you the roots and times a pure exponential. The same results we obtained in 2010 in a joint paper with McIntyre and Giuseppina Terzo. We reproduced the same results as Hanson and Rubel and Katzberg for any pseudo-exponential field of Zilber, actually even for a wider class. And some related independently was obtained also by Auascope with completely different methodology. And of course, we don't use any analysis, and we use only algebraic methods and results which come directly from the axioms of Zilber. In 2006, Marker considered a very simple exponential polynomial. So you take a polynomial in two variables, irreducible and which depends on both variables, and you can consider it the function, a unary function over C, defined in this way. So this means that this polynomial is just an exponential polynomial with one iteration of exponentiation. And it showed that this comes from analysis, that it has infinitely many zeros. It's Hadamard theorem, because this is it can be applied Hadamard theorem. So this is not a great result, and he has it for any no restriction on the coefficients of the polynomial. Assuming Shannon conjecture and restricting the polynomial P to coefficients in Q-alg, so with algebraic numbers, he showed that there are infinitely many algebraically independent solutions. This guarantees that there is, it's a technical thing, you have to believe it. It guarantees that we can interpret the result of Marker as an instance of this exponential closure. This is just a variety. I go back and see. No. Sorry, this ring is a. So the variety is given by z e to the z. This is you consider z in C. You consider this the intersection of the variety with the graph of exponentiation, where the variety V is that this one is determined by P of x1 equal to 0. So So it's a very simple case of the fourth axiom of Zipper, and it shows that under this hypothesis, is a strong hypothesis, that there are infinite many algebraic solutions, but this is equivalent to say that in this intersection there is a generic point. So a generic point is a point which belongs to the variety, and it has the same transcendent degree as a tuple as the dimension of the variety. This is one, and this one, this as dimension as transcendent degree 1, but this is a stronger, much stronger property. And Mantova last year improved the marker result by eliminating this hypothesis on the coefficients of P. Still a Shannon conjecture is needed, but there are infinitely many algebraically independent zeros. Now these properties, I want to go back to that, to the axioms. You need to talk about infinitely algebraically independent solutions in order to have that the point is generic over any finite subset. If you take A is a subset, finite subset of A, you consider the field generated by A, and you want that that the variety intersects the graph of exponentiation in a point which is generic over any finite extension of Q inside C. So this is much stronger. Of course, if I say that there is a generic point, this is immediate, because there is an algebraic relation between Z and the e to the Z, which is given by, because it's a solution of this polynomial, so the dimension is 1. But you want that this is over any finite extension of Q. And you have guaranteed this if you require that there are infinitely many algebraically independent solutions. So, next. Then this is we considered in a joint work with Fornasiero and Giuseppino Terzo, we consider the next case after marker, so with 2 iterations of exponentiation. Already with this, a general case is, for the moment, is out of reach. So just a bit of notation. With this, we denote k plus 1 iterations of exponentiation. And so f is the polynomial evaluated in z, e to the z, and so the k towers of exponentiation. And this is the definition, the general definition of a generic, of a point generic, that I tried to explain before. So a solution of f is generic over L, a finitely generated extension of Q. Of course, this has a meaning if you include in this extension the coefficients of the polynomial. If the transcendence degree of this tuple is maximum, where k is the number of iterations of exponentiation. So the problem is that in some cases that I will say later, we are not able to guarantee that the transcendence degree drops. It may drop too much. We cannot guarantee that there are not algebraic relations. For some cases, yes, but not for general. So the conjecture is that if we take any L, a finitely generated subfield of C, and this is a non-zero irreducible polynomial, which depends on the first variable and on the last. In this way, we exclude that is an invertible element, because there is the presence of this x, so it's not a purely exponential polynomial. And there is the last one, so we have exactly k iterations of exponentiation. So we want to show that there is a solution which is generic over L. And the strong exponential closure of Zilber implies a positive answer to this. So this is just an instance we can consider this of the axiom of the strong exponential closure, but still is not known too much. What we can prove is that if we consider, or assuming Shannon conjecture, and with the same restriction as the original, the first result in this on this field by marker, that the coefficients are in Q-alge, and at the moment we cannot eliminate this hypothesis. So this polynomial is a non-zero reducible. Then there exists a generic solution over Q. So it's not full. It's not over any finite extension of Q. We would obtain that if we are able to prove that there are infinitely many algebraically independent solutions. As we still cannot do it. So I hope it's clear that having this, that there are infinitely many algebraically independent solutions, implies this, that is generic over any infinitely generated extension. It's just a calculation. Okay, these polynomials have always, we exclude the trivial cases that we can deal with either Katzberg or Hanson and Rubel, because we are not interested in this. And for the proof of this result, we use a refinement of a result of Masser, which guarantees the existence of a solution of a system like this. These are polynomials, classical polynomials, and on the left side there are purely exponential. So under certain hypotheses, using certain tools, Masser showed that this system has always a solution. And this corresponds to show that the function f, defined in this way, has a zero in C. I put a slide of what is needed, but maybe I just skip it, so otherwise I don't have time. What is used is this theorem we found. We reproved the Masser theorem because we needed some special cases also for later. And we used this result of Kantorovich, which is for functions, entire function from Cn to Cn, that under certain hypotheses on the Jacobian and over the Hessian, we have a solution nearby a point. And we have to identify where is the point, and the point we find that this system, in our context, this system has infinitely many solutions, which are on a lattice. This condition is needed in order to guarantee that near the point we want, the polynomials don't get value 0, because otherwise you would never be able to solve this. If you have the polynomial equal to 0, the exponentiation is never 0. So for this, we consider first this case of a simple. We have a couple of polynomials. I showed just some details on this case. We take a polynomial with two iterations of exponentiation done just in this way, and we want to show that there is a generic solution over Q, so that the tuple, the solution lives in 4 space, and the second two coordinates are non-zero. So the variety which is associated is this one. We consider, we work in the fourth space, and we impose that the first and the last coordinates are solution of the polynomial, this polynomial, and we impose that the second and the third coordinate are equal. So we are considering Z1, Z2, W1, W2. And we have that this one and this one are solutions equal to 0, and we require that these two are equal. And so this is our variety, which has dimension 2. And the proof, no, I just catch, because as it is, you don't see where the master system is used. The master system is used here in this context. First of all, we can show that there is always a non-zero solution, because otherwise you have that E is algebraic. Second, we distinguish two cases. If W and E to the W are linearly independent, then we have a generic solution. Because by Shannon conjecture, we have that this is the input, these two, W and E to the W, and then we have to make the exponential of the input. This is greater or equal to the 2, which is the linear dimension of the pair W, E to the W. And it's actually 2 because this W and the E to the W are algebraically dependent because they are solution of P of xy. So the dimension is exactly 2 as the dimension of the variety. It's written here. The thing to avoid, what we don't want is that W and E to the W are linearly dependent. So we want to guarantee that there is always a solution where W and E to the W are not linearly dependent on Q. And we do this using the master system. We construct a system a la master. So we get a contradiction. Assume that these are linearly dependent, then making some substitutions, and we can observe that W is always transcendental, because otherwise we would go against Lindemann-Weierstrass theorem that I mentioned at the beginning. And so assuming that there is this linear dependence between W and E to the W, we go down to this relation, where these n and m are integers. So we deal with a polynomial Q of this form. So our starting root of the polynomial Pxy is also a root of Q. And Q, it can be or these other polynomials the same. I just concentrate on the first case. For the second one, we argue in the same way. So this polynomial, you can prove that is irreducible. And the variety associated to it has dimension 1. So the solution is a generic solution for this polynomial Q, and is also generic for the starting polynomial. So these are two irreducible polynomials which have a generic solution in common. This forces to be equal. So P and Q are forced to be equal. So P, if there is the linear relation between the W and E to the W, is of a certain form, as this form, and this S is determined by P from the beginning. So what we do is we construct, this is a little system a la master, which guarantees that we put ourselves in the hypothesis, so we are in the hypothesis of a master, this has a solution, and if you do the calculation, this condition here guarantees that there is no linear dependence between E and E to the W. So we find always a solution of the starting polynomial where there is no, we avoid this relation, which makes, this doesn't happen. We can always reduce ourselves to a case where, to the first case, where there is no linear independence, where this W and E to the W are linearly independent, and then we get a generic point, generic solution. So we for the other case is equal, and then we skip this. We obtain the same for another case, making it a bit more complicated, but the arguments is always the same. The argument is the same. It's just we need an ad hoc system of Alamaster, a bit more general. And the argument here is a bit subtle, because it's not that we get, again, we go back from the linear dependence. If there is a linear dependence, we don't get that the starting polynomial assumes always a form as if x to the n as before. But we have finitely many possibilities via calculation. And what we do is a generalization of master system, requiring that the solution does not satisfy one of the possible finitely many cases. And we have guaranteed then that there is a solution of the starting polynomial, which is whose input and exponential are not linearly dependent. The general case is this one. But as I was saying before, we can exclude that for the general case, we find a solution whose transcendence degree of the tuple is not 0, is not 1, and is not k minus 1. And this, if you take k equal to 3, this gives a complete answer for this polynomial here. But for the general one, we don't. We're still working on this. So we cannot exclude the other cases. There can be other relations, algebraic relations. Always a Shammer conjecture is needed, and also the coefficients are to be in QH. Well, I think I stop here, because then there was something completely different. So I spoke only about the first 3 of the points. I started at the beginning, only one. Okay, I stop here.
Thank you. Any questions or comments? Even in French, live.
Not in Russian.
Just a little question, Paola. When you say the best we can prove, it is the best we know prove, yes.
We know how to prove, but no,
yes,
it's not
know.
that is, we aim
Yes.
to prove that this is,
Yes.
that it doesn't drop.
Okay.
So if we want to play with these polynomials, what is the method to prove that they are irreducible, for example? You have a method? Or is it,
No, we assume that it's irreducible because, no, if you take a polynomial which is not irreducible, there is a result, I was going to mention this later, but there is a result of originally of RIT going back to 1927, which gives a kind of unique factorization of exponential polynomial. A kind of, because you can, he proved, but he has the result for exponential polynomial only with one iteration of exponentiation. So if I take this, he shows that this Sn and Q1, Qk, where these polynomials are irreducible and these are unique. And this one are what he calls simple polynomial, which is a bit more technical. And on this, this polynomial means that you can, if you work over the exponents, you consider the Q vector space generated by the exponents in an exponential polynomial. Those polynomials which have whose exponentials have generate a dimension 1 Q vector space are called simple. An example, if you take x minus y, this is a simple because modulo because it is length 2. Everything which is length 2 is simple. But what happens for this one is that these polynomials have can be factorized in infinitely many ways, because you are allowed to have fractional numbers and the exponentials. So you have x1 upon k minus y1 upon k, and whatever it is for k greater than 0. But then in k, you have different factorizations. So what he showed, this is a this is a 7, and this is a 2. He showed that this part is unique. This is the classical irreducible factors, and this part is a product of simple polynomials, where each one of these, of course, is not irreducible, because you can factorize in infinitely many ways. But what the difference between two of them in the factorization is that the Q vector space generated by two different ones are different. You don't pretend to factorize them. You just divide them according to the Q vector space of the exponentials. And this is needed for, is a very useful characterization. He did it for where this has an exponential only one height, but it can be generalized to any exponential polynomial of any height.
And for the questions? Okay, so again. Let's move on. Juan José Loureiro. Lipschitz determinacy.
Let me start by thanking the invitation for me an honor to be at this conference. I'm going to be talking about Lipschitz determinacy for initial levels of the Hausdorff hierarchy in second order arithmetic. This is a joint work with Andres Cordon-Franco and Felix Lara Martin from the University of Sevilla. Well, I'm from Lisbon, Portugal, not Spain. We were inspired by the work of Wage. He, in his PhD thesis, tried to, well, he did classify the complexity of subsets of real numbers, and we tried to use his ideas to calibrate the strength of Lipschitz determinacy as well as the semi-linear ordering principle for initial levels of the Hausdorff hierarchy in terms of subsystems of second order arithmetic. So I'll start off by introducing some concepts, definitions and state of the art, then the formalization of Lipschitz games and strategies and determinacy in second order arithmetic, an overview of the results and the methodology we use to prove the results, Lipschitz determinacy for the very first levels of the Hausdorff and Wedge hierarchy, then the dichotomy principle, which is a principle we needed for get Lipschitz determinacy for open sets and closed sets. Then the main result is a reverse mathematics result, and then I address some technical questions. The classical games are the so-called game-steward games. These are infinite two-person games where both players play alternately natural numbers, and they build a sequence, an infinite sequence. There is a set, a pair of sets, which is defined in the start of the game, and the winning condition for player 1 is when the final sequence belongs to A, player 1 wins, otherwise player 2 wins. So Lipschitz games are similar but also different. Here we have two sets, and each player plays with one of the sets, and the winning condition for player 2 is as follows. Player 2 wins when the sequence built by player 1 belongs to set A, if and only if the sequence built by player 2 belongs to set B. Otherwise, player 1 wins. Well, there is the possibility of reducing Lipschitz games to Guessword games. Player 1 wins a Lipschitz game for A and B, if and only if player 1 wins the Guessword game for the negation of the equivalence between A and B. But this reduction comes with a price, and the price is the increase of the complexity of the payoff set, and that can be a problem in second-order arithmetic, since second-order arithmetic is kind of limited for the for Guessword games, as we shall see.
In what system does this equivalence prove?
In
what system you prove this equivalence between of two games?
This equivalence?
Yeah.
We use this reduction when the sets when the determinacy for Guessword games is given in second-order arithmetic, and this goes only to delta 3, delta 4. Then we don't have more Guessword determinacy in second-order arithmetic.
Yeah, I understand. So what this equivalence itself, so what system do you need to? So it's perhaps you can say SCO or it's
SCO.
Ah, yeah, okay,
Yes. Now the games are determined mean that one of the players has a winning strategy, and this fact is not mandatory, so we have to stipulate it with an axiom. There is the so-called axiom of determinacy. There are axioms of determinacy restricted to classes of sets. Wedge, in his work, used determinacy, or assumed Lipschitz determinacy for all Lipschitz games, and this the determinacy turned out to be very important because it has very important consequences, like the regularity principles, the countable axiom of choice, and well, it contradicts the axiom of choice, the full axiom of choice. Well, for completion, just I refer that there is a conjecture, eventually due to Solovay, which is open, stating that the axiom of determinacy, the full axiom of determinacy. Yes.
I slightly duped in the last case, because if you have uncountable, the last AC omega of x to the omega.
Below.
The penultimate level.
Second line from below.
Yes. Second line from below. No, below.
Second from below.
Second from
below.
Yeah, and yes.
And the last symbol.
This one.
This one.
So, I'm not sure that this is true. Because if x is of size omega 1 or more, that probably this is not true.
Well, this
actually I have a bit forward, but it seems this is
this a recent result from Andret. He showed this in script theory. Yes.
Okay, I see. Maybe we should have some restriction on x.
This one.
Yes. So it seems if x is of size omega 1 or more, it is incorrect.
For x, just for x.
Yeah.
The decision here is I think the exponent is not correct. So the exponent
should not be there.
Yes.
Well, he speaks of the cardinality, no?
But anyway, I think we are not. This is not the central question of the
Yes.
right?
Yeah.
So let's go.
Please continue.
In his thesis, Wedge was not concerned with the determinacy of Lipschitz games. He just studied the so-called reducibility relation. So A is Lipschitz reducible to B if and only if there is a Lipschitz function such that A is the preimage of B under this function. And with using this relation, he defined Lipschitz degrees and obtained a very fine hierarchy of classes of sets of real numbers, there are non-self-dual degrees like this one and this one. So and self-dual degrees where there is just one class, we tried to study Lipschitz determinacy for these initial classes of the Hausdorff and of the Wedge hierarchy. Wedge soon realized that the SLO principle was important since we can deduce important results from the SLO principle, similar to the results we obtained from the axiom of determinacy. The SLO principle states that A is Lipschitz reducible to B, or the complement of B is Lipschitz reducible to A, and this is the structure of hierarchy, so to say. Recently, Andretta showed that in Zermelo-Fraenkel set theory with Baer property and dependent choices, we have the equivalence between Lipschitz SLO and Lipschitz determinacy. These results can also be obtained in set theory without the axiom of determinacy. There is the classical result of Martin telling that the Gage-Stewart games are determined for real sets. Now going on to the second order arithmetic, there is the classical result of Friedman stating that second order arithmetic cannot prove that all real Gage-Stewart games are determined. And there is a recent result of Montalban and Shor, which states the optimal bound for determinacy in second order arithmetic. There is also a very detailed picture of the reverse mathematics for Gage-Stewart determinacy, which was obtained by the results of Steele, Tanaka, Nimoto, and Metzelem. So, in contrast, we don't have this detailed picture for Lipschitz determinacy, and we have the theorem of Levaux and Saint-Rayman stating that all Borel-Lipschitz games are determined, but as I said, there is no detailed analysis of the strength of Lipschitz determinacy in terms of subsystems of second order arithmetic, and the reverse mathematics of SLO hasn't been investigated either. So we have only the reduction from Lipschitz determinacy to Gauss-Stewart determinacy, and this gives us an upper bound for determinacy, for Lipschitz determinacy, but this bound needn't be optimal. So this we regard it as a gap in the understanding of reverse mathematics of infinite games, and we try to close this gap in second arithmetic. So we need the base system in second arithmetic. It was already explained before in other talks. Then we can codify metric spaces, in particular Cantor space, which is the set of all sequences of series commands endowed with the product topology inherited from the discrete topology over 0 and 1. And we can prove in RCO Wedge's lemma. This is very good because Wedge's lemma allows us to use Lipschitz games instead of the reduction, the reducibility relation. And as of this point, we can always use Lipschitz games instead of this reducibility relation and the Lipschitz functions. Then we also need the WKLO system. Using this system, we are able to show that trees for which characterize delta 1 sets can be pruned. This is important for our proofs, and system SCAO will also be important for